Hey everyone, and welcome back to part 2 of this video on pipe flow. In the last part we introduced the Darcy Friction factor. In this part we'll explain how you can calculate lambda yourself. In the previous video we introduced the Darcy-Weisbach equation. This equation to calculate the frictional head loss caused in a pipe is an extremely important one. Of the variables which make up this equation, the Darcy Friction factor, lambda, is one of the more complicated ones, and therefore let's take a look at how you can calculate it in the event it's not given to you as initial data. This proportionality factor depends on two major groups of variables, flow regime and pipe material. Let's begin by taking a look at flow regime. There is a variable with which we can classify the nature of a flow based on some of its essential properties, and this is known as Reynolds number. A fluid's Reynolds number is used to classify various types of flow regimes even when using the same fluid. But what do we mean by this? We're referring to the difference between laminar and turbulent flow, and we can demonstrate this with Reynolds' experiment, which you can see here. By running the line of blue dye through water, this allows us to follow the differences in internal movements of the transparent fluid. Here we can see two examples of flow. On the left, we can see a laminar flow, where the flow is smooth, orderly, and there's little tendency to mix between the dye and the surrounding fluid. Now, in contrast to this, if we look on the right, we can see a turbulent flow, which is random or chaotic, and where the dye tends to mix with the water around it. We can estimate the flow regime a fluid is running in with Reynolds number. What Reynolds number the flow in the pipe is being run at naturally has a large impact on how efficient the flow is, or in other words, how much or how little energy the flow loses in transporting a parcel of fluid from one place to another. As you can see here in the middle, a flow inside a pipe with a Reynolds of less than 2000 is considered laminar, over 4000 is considered turbulent, and in between the two is considered transitional. This number is defined by the equation which you can see here, and also a way you can re-express it. Both these expressions being the same, with the difference being the first is in terms of dynamic viscosity, whereas the second is in terms of kinematic viscosity, which is in turn defined as mu divided by rho. For the purpose of this video, we'll focus on the latter expression. It's important to note the kinematic viscosity of a fluid is not only determined by which fluid is being used, but also the temperature it is flowing at. Now that we've briefly introduced flow regime, let's cover the second major group which affects our Darcy Friction factor, pipe materials. Although for our pipe rig in the previous video it was made entirely out of PVC pipes, there are a wide range of materials used in piping such as cast iron or even concrete. Naturally, the properties of these materials have a large role in determining the friction which occurs between them and the fluid inside. Again, we have an equation with which we can quantify these material properties. This is known as the relative roughness of the pipe and is determined by two things. The first is the diameter of the pipe, as the geometry plays a role, and the second is effective roughness. This variable is material dependent. Reference books and online sources provide tabulated values of effective roughness for all the commonly used materials in pipes. So now that we have the two variables which define a Darcy friction factor, how do we relate them? This is known as the Moody diagram, and it's based on a large number of experiments carried out in a systematic and controlled manner. I know the number of lines can initially make this look quite complicated, but it's actually very simple. As you can see, two of the axes are quantified of flow regime on the bottom in terms of Reynolds number and relative roughness on the right. Now that we know the formulas with which we could work these out, let's make up a brief example. Let's say we know the pipe is made out of PVC. This allows us to select our corresponding effective roughness. And we know that our pipe is 15 mil diameter. With these two values, we can calculate our relative roughness at 0.0001. We are then told the fluid is flowing at a speed of 1.3 meters per second, that the fluid is water, so we'll use this approximate value for kinematic viscosity of water. We now have all the information we need to calculate our Reynolds number, which comes out as 2 times 10 to the 4. With that information, we can now go back to our Moody diagram. We can begin by marking on our two axes the values we calculated. Now you simply follow the curved line that matches your relative roughness up to the point where it is directly above your Reynolds value, and then you mark the spot. You can then read horizontally across to obtain your Darcy Friction factor. Naturally, this is easiest if your relative roughness falls exactly on one of the curved lines. Well, let's imagine it doesn't. Just do your best to remain between whichever line is above and below, and you should keep a good approximation. The Moody diagram provides a quick and effective manner of obtaining an approximate value for your Darcy friction factor. This should allow you to perform your frictional head loss calculations. Hopefully you've all followed this short video. In the next part, we'll be introducing another source of head losses which occur in pipes, known as local losses.